Good morning, scholars. Today we're going to embark on our first official calculus lesson, and it's a big one. This is 1.2. We're going to introduce the idea of a limit. We're going to learn how to write limit notation. We're going to be able to evaluate limits based on a graph, and we want to be able to convert between mathematical notation and normal English. Additionally, we're going to hit one more standard, and that is to distinguish between the value of a limit and the value of a function at a given point, or a given x. This idea of a limit is one of the three big ideas as designated by the AP board. You may have noticed on the syllabus I added a fourth. That's just me, that's not the AP board. But whenever we introduce a big idea from the AP board, it's going to be really important because generally, they only listed three big ideas for the entirety of the course. And whenever they introduce a big idea, what they're going to want to do is they're going to represent it in as many ways as possible. So in all cases of the big ideas, they are going to want to represent it in an algebraic, a graphical, a verbal, and a tabular way. A tabular means table. Today, we're going to introduce the idea of limits, and we're also going to discuss how to convert them into, just basically talk about them intelligently with normal English, and then we're also going to look at what they look like visually on a graphical representation. Okay, here's our first example. One of the pillars of human intelligence is the ability to observe, recognize, and extend patterns. So if I ask you this question, what I've done here is I've taken a normal linear function and I have blocked out a piece of visual information to you. And what I'd like you to do is I'd like you to predict or guess the value of f of 3. That is, what is the function's height at an x value of 3. In calculus, these ideas are not as straightforward as you might think they are. So most of you would probably say, okay, well, it's got a slope of about a half there. So that means that if the line continues as I suspect it would, we'd end up right here. An x value of 3 would trace up the graph right there, and we'd go over to an x value of 4. So the function's value at 3 is 4. The issue arises is when we look at things that are a little bit more exotic. Like if we look at this function right here, where that missing spot right there, if we trace up an x value of 3 and then we notice there's an open circle there. So that would mean that the function is actually undefined at an x value of 3. This is a regular occurrence where just some weird stuff happens near x values, and limits allow us to both describe and in some cases evaluate the behavior at these very strange points in the graph. If we look at another equation, here's a verbal description of what a limit is. As the x values get closer to 2, what is the height of the function doing? So as we approach an x value of 2, so as we're coming in from both sides on an x value of 2, how high does the function get? Well, that means that if we were to trace along the function is increasing from the left and decreasing from the right, and it's arriving at an overall height of 4. So one would say, as the x values get closer to 2, the height of the function is getting closer to a height of 4. Okay? And that is pretty much exactly dead on the language that you need to use. This is the official language right here, the phrase that you're expected to state or write whenever you're communicating to an AP reader. So as x approaches 2, f of x approaches 4, or the height of the function approaches 4. And that basically just means exactly what we drew out here. As we approach an x value of 2, the height of the function is approaching 4. So as we come in on 2, the height of the function is coming in on a height of 4. So in addition to verbally, we also need to be able to express this mathematically. So we're going to use some symbols for that, okay? And this statement right here with this limit notation says the exact same thing. It has basically 4 main components. One is that it has this symbol LIM, stands for the word limit, the limit, and then we have to designate what x value we're approaching. So in this case, we are approaching an x value of 2. We have to say which function are you worried about? So in this case, our function's name is f. And so you have to write down that the function's name is f. And sometimes you'll see that the function is written out explicitly right here. So there might be a function definition right there. And then we have to say what our answer is. Okay, so those 4 components come across in every what we call a limit statement. Okay, and this is again equivalent to the verbal statement as we saw before. You can see how each one of those pieces come together. So we have the limit right here and right here, we have of f of x. So what function are we talking about? You see right there and there. We've got as x approaches 2, so we've got all those words expressed in those three symbols right there. We got an equal sign, which is the word is, and our answer, or our height of the function at the end of it, of 4. Now again, this is as we approach 2 from both sides of the function. This is called a general limit. When we approach the function from both sides, that is, we approach from the left and we approach from the right, so the left and the right at the same time, we call this a general limit that comes from both sides. Now, from that statement, you might infer that there are limits that do not come in from both sides, and you'd be absolutely correct. They're called left-hand side or right-hand sided limits, right-sided limits or left-hand sided limits. And the way we designate those with notation is with a little minus or a little plus right there. That is the only difference. In this case, I've drawn a slightly different graph, and you can see that these two limit statements are absolutely true. So what this little minus sign means up in the superscript, now notice that it's also after the x value. It is not before the x value. What that little minus sign means is that we are approaching from the left. So that would be us traveling upwards on the graph in this direction. And you'll notice that that leads to a height of 3. Even though the function is not defined there, the limit as we get exceptionally close to 3 becomes a height of 3. Now I'll switch colors for the other one because it's important to distinguish. Now this one, see the little plus sign there, that means that we're going to approach the x value of 2 from the right-hand side. So we're going to look at the function right here. It's a constant function, and it is constantly at a height of 4, especially and including when we get to an x value of 2. And again, this means that we're approaching from the right and traveling leftward on the graph. You'll notice in this particular question that the left-hand limit and the right-hand limit do not agree with each other. So if we were asked the general limit coming in from both sides at the same time, so a third question could be asked, if we come in from both sides at the same time, well, on this one we're approaching, on the right-hand limit we're approaching a height of 3, and on the left-hand limit we're approaching, on the right-hand limit we're approaching a height of 4, and on the left-hand limit we're approaching a height of 3. So those disagree with each other. So we would say that the general limit does not exist. And that leads us to our definition of a general limit. Okay, so we have this slide right here. I'm going to actually insert here general limit, definition of a general limit. And it basically says the exact same thing that we just said. If you look at this, it says if the left-hand limit exists and is equal to the right-hand limit, then the general limit, where there is no plus or minus sign above that C, exists. So that means a few things. One is that over here on the left-hand side limit, you have to be able to evaluate that to the point where you actually get a finite value, a number. And that number must match, which means that the right-hand limit must also exist and be a finite number. These two things have to be equal to each other. And if those two are in total agreement, then the general limit, the one without the plus or the minus sign above the C value, then that limit exists and is equal to whatever number you got, okay? If we examine a function where the values are infinite near the x value that we're approaching, then we say that that limit does not exist, even if it's just like a left-hand or a right-hand limit. It's pretty tough for a general limit to exist. There are more conditions under which a left-hand limit and a right-hand limit exist than there are that the general limit exists. So this is the most special. And then the left-hand and the right-hand limit existing is less special. Let's look at an example. Here's our first example. You can see this is a situation where we're talking about a pretty funky graph. Let's work, all these questions over here are about an x value of 7. So let's look at our first couple questions. We'll zoom in as much as we can. Okay, so this limit notation says as we approach an x value of 7 from the left, so that's like this. What is the height of the function doing? Well, the height of the function there, if I traced it all the way over, would be 3. Okay. This limit says if I approach an x value of 7 from the left, so I'm going this direction, you'll notice that those two are in agreement and the height also approaches 3 at that point, because I would trace that over to the same spot if I were to trace it from the right. So now when we look at the general limit, as we approach x value of 7 from both sides, do the left-hand side limit and the right-hand side limit agree. Well, look at right here. We wrote it down. We can also see it visually up in the graph that yes, they agree, and that value is 3. The last thing that we need to do today is be able to distinguish between a function value and a limit value. In this final question right here, we're asked what is the function's value, g, at an x value of 7. So we go to an x value of 7 and we trace up until we find something solid. So either a filled in circle or a line or a bar or a curve or something like that. But you'll notice there is no such thing there. It's an open circle. So we say that this function value does not exist. Okay, now let's take a look at what's going on at an x value of 4. Again, we're asked a left-hand limit and a right-hand limit and a general limit. If these agree, if the left hand agrees with the right, then the limit exists and it's a number. And then finally, we're asked the function's value. So let's approach it. Let's do the first one. We're approaching from the left. If we approach from the left, the height of the function is dropping to a value of -1. If we approach it from the right, we're coming this way, we're decreasing to a height of +1. Now, +1 and -1 are not the same number. So our left-hand limit and our right-hand limit disagree with each other. So therefore, the general limit, as we approach 4 from both sides, does not agree. So we could not write down a single number that describes what the height of the function is doing as we approach 4 from both sides. So it should make logical sense that that limit does not exist, as well as sense according to the definition of a general limit. Okay, lastly, we are asked what is the function's value at an x value of 4. So here again, we're going to look at an x value of 4 right in here, and we're going to go find the solid piece of the function. This is hollow, meaning it does not exist there, but there's our filled in circle right there, and their height is. Again, we ask that question at the very end to distinguish between the value of a limit and the value of a function. It's important to know the difference. On that last example, we had a general limit that does not exist. And calculus tends to focus on the weird sections of the graph, the more complicated sections of the graph, rather than the easy sections of the graph. So I want to understand why that limit did not exist. That limit didn't exist because as we came in from the right and as we came in from the left, it came up with 2 different values. Okay? This type of, discontinuity in the graph is called a jump or a step discontinuity. It's a fairly common occurrence, and we should know basically anytime we see one of those on the graph that the general limit is not going to exist. What I'd like you to do right now is I'd like you to pause the video and I want you to see if you can sketch out in your head or on paper if you can create another situation where the general limit will not exist. I'm going to show you a graph where there's a few limits that don't exist. Okay? Here is a rational function that's been graphed for us. And I've asked you about its behavior near an x value of -2 and an x value of +2. And you can see all these positives and negatives starting to pop up over by the x approaches number. So there's a negative out front to indicate that it's a value of -2, and there's a negative up in the superscript to tell you that you're approaching that from the left-hand side. So be able to read that well. Now, what is important here, let's take a look at this very first one. We're going to approach a value of -2 from the left following the graph. Well, what's happening to that graph? That graph is dipping downwards, and you can see that orange line is indicating a vertical asymptote, indicating that that graph is extending down towards maybe what you call negative infinity as you approach a value of -2. That means that when I try to evaluate this limit, I do not get a number. Because I don't get a finite number, the answer to this is this value doesn't exist, okay? But we're going to maintain the practice of being slightly more specific. So instead of do not exist, we're going to actually describe what direction it's going. So we're going to go ahead and start working with infinity. That's kind of the fun part of calculus, is we're going to start thinking about infinity in a new way. So maybe if I were to ask you to write down a symbol that represents what this function is doing, maybe you would say it is approaching negative infinity, something like that, or the figure 8, however you want to draw your infinity symbol. And that's actually the most specific correct answer that you can do for this question, okay? So the negative infinity symbol, okay? But I don't want you to think of infinity as a number, okay? So we're actually going to go over here, and I'm going to define this negative infinity symbol that we just used here, okay? We are going to call this, we're going to say that this means that it is decreasing in an unbound manner. Sometimes we say it is decreasing without bound, or it is approaching negative infinity, but officially speaking, that's what we're going to say. We've encountered some unbound behavior and it is tending towards negative infinity. So just the converse of that, or the opposite of that, would be that if I put down an answer that says infinity, that to us means that it is going to increase in an unbound manner. Okay, so those two definitions of infinity, that symbol, infinity and negative infinity. Like, remember, infinity is an idea, not a number. Okay, now let's take a look at, I'll change colors for this. Let's see, let's go for approach -2 from the right hand, and you'll notice that as we go that way, well, now we're going up. So this is actually going to be best answered by infinity. Now this limit does not exist because it's not a number, but we can go slightly more specific than that and say that it is increasing without bound in the positive direction. And lastly, we are asked to evaluate the general limit. So this one doesn't have a little plus or minus on the superscript. And since we have disagreement here, right, those two are very different things from each other. One, it's increasing or decreasing to infinity on one side or the other. So for sure it doesn't exist. But also, because they're going to two different places, the best we can do here is we can say that the limit does not exist here. Okay, let's examine what it looks like at the x value of +2. So again, I'll switch colors here to blue. And this time, let's go from the left, an x value of 2. So we're going to go up, and you'll notice that that is increasing without bound. So I'm going to put down that infinity symbol. If I go from the left, okay, so we're going this way. If I go up the graph that way, you'll notice that I'm also increasing without bound. And you might notice now there is agreement between these two. Okay, so because I didn't get a number in any one of the three cases here, either the left hand, right hand, or the general limit, I know that the limit does not exist. Okay, so the limit, just to be clear, for all three of these does not exist. However, I can be slightly more specific than that and say on the left side and the right side, they both increase without bound. So this is the best, most specific answer for that question. The last question I have actually has to do with going out as far as you can to the right and to the left. So this is going toward as x approaches positive infinity. What's the graph doing? You might notice that there's a horizontal asymptote here this time. And that horizontal asymptote comes in at a height of about 1.5. So as I tend further and further and further to the right, that is going to, according to what the graph suggests, it suggests that it's going to get closer and closer to a height of 1.5. And if you look again on the other side, if we go towards negative infinity, an x value of negative infinity, again, we have that asymptotic behavior on a horizontal, and that's going to, again, approach a height of 1.5. Our last example today hits hard the ability to talk about limit notation and behavior in a way that would be clear to an AP reader, say on an FRQ question or something like that. So in this question, I asked you to write as many limit notation expressions as you need to completely describe the behavior of the graph near x equals 3. So that's like right here. How do we describe that behavior using our new tricks? Every time I write a limit statement, I also want to back that up with a verbal statement that basically says the same thing. And I also want to explain why the limit does or does not exist as we approach an x value of 3. So why don't you pause the video right here and see if you can write down some mathematic notation to describe the behavior of the function near an x value of 3. And I'll give you a hint. I used 4 expressions. Okay, so if we look at the graph here, we notice that as we come in from the left, that approaches a height of 1. So I'm going to write a limit statement that says that. I'm going to say the limit as x approaches a value of 3 from the left of the function, in this case it's called h, is a height of 1. If we approach it from the right, so we're going this way, traveling this direction, then, so I'm going to write that down, limit as x approaches 3 from the right-hand side of h of x, then it looks like I'm a little higher. Then I go to a height of 2, sorry. And That would mean that if we did the general limit, so here's a third limit statement that I could write, that would indicate that the limit, since we have disagreement between the left-hand side and the right-hand side, does not exist. And I said I was going to write 4 statements, and that's because there's a little jobby up there. And I would just like to show the reader that I know what I'm talking about and say, hey, the value of the function at 3 is a height of 3. So we have a situation where we have a left-hand limit not equaling a right-hand limit, which causes the general limit not to exist, and yet the function is still defined at yet a third spot. So those 4 statements together give the reader, if they didn't have a picture of the graph in front of them, it gives them a really good idea of what's going on with the graph. Okay? Now we've already translated these phrases, these limit statements, directly to English, so I'm not going to write that out here, but I'll say it verbally. The limit of h of x as x approaches a value of 3 from the right is a height of 1. Okay? So you do that for these 3 limit statements. I do want to explain in words why the limit does or does not exist. And in fact, I might even do it in mathematic notation because you're allowed to do that, because it shows off that you know what you're doing. So what you can say is, you can say the limit as x approaches 3 from the left-hand side of h of x does not equal the limit of h of x as x approaches 3 from the positive side. And then you can say, therefore, the little 3 therefore dots, the general limit, h of x, not f of x, I'm so used to writing that, does not exist. So those symbols right there together give a full and complete description of why the limit does not exist. And if you were to write that out in words, you just write out in words each of those statements. The left-hand, you could also write it down as the left-hand limit is not the same as the right-hand limit, so therefore the general limit does not exist. This problem concludes the lesson for the day. Your assignment is posted up on the website and Schoology, and then there is a Schoology assignment that asks you to report a few answers. I will see you next time.